And now, Procter Gamble, Kevin.
Thank you. As you can see, the title of our talk is Statistical and Optimization Techniques for Laundry Portfolio Optimization at Procter Gamble. And this was contributed to by several folks that are listed here: Natalie Esquejo, Kevin Miller, and myself from Procter & Gamble, and then Ivan Oliveira, Rob Pratt, and then also Meng Zhao from SAS. The goal of this project, was to set the portfolio strategy for our multi-billion-dollar laundry powder business. And really central to this, as you'll see, is it was about cost and then also about complexity of our operations. And the focus for this is going to be on a project that we worked in North America, which contained 20 different products in the portfolio. Traditionally, to approach a project like this, what people would do to reformulate a portfolio is you look at it one product at a time. And even classically, if you look back, people would do physical prototyping and also physical quality testing of this. We realized that there was, a lot of opportunities for analytics really to improve this work process, to drive efficiency, and to make, the results and solutions that we could find even better. And we were going to do this by, first, doing virtual prototyping for the actual product creation, and then also virtual testing of this by using modeling approaches. And then also we'd be able to use some of the innovative approaches in mathematical optimization that you're going to hear about today that would for the first time really allow us to kind of look at this as a system-wide portfolio optimization as opposed to this more sequential product by product type of a work process. As far as the problem structure that we were dealing with and the actual mixing procedure that's used for the detergents, we make a large number of products. As you can see over here for the North America example that we're going to talk, it was about 20 products. And we make those from a much smaller number of these common intermediates, which are shown kind of at the second layer up with the colorful circles here. And the way that this is conducted is each product is made by selecting exactly one of the common intermediates and then as many of the different finishing additives as you need in order to get to the required finished product. Now, the actual cost of the overall portfolio really depends upon the premixes, how many of them are used in creation of the portfolio, and then the product properties that we care about, which are things such as the stain removal and the whiteness and the density and all the different characteristics of the detergent. Those actually are predicted via the composition of the finished product. And that's kind of what's listed on the second layer down from the top, which is SRI, which stands for Stain Removal Index. Now, the goal of this, the production goal, was to minimize the total cost across the entire portfolio. And we did that subject to constraints around the actual levels of stain removal and whiteness and density for each of the different products that were in here. So in a way, you could think of as kind of defining the identity of that portfolio product by product. As far as decisions to be made, we wanted to make sure that we could decide which product was assigned to which of these intermediates, so an integer decision. And then we also wanted to decide what the composition of the different intermediates was, as well as the level of the intermediates and also the level of the different finishing additives that were used. Before we really dig into any of the math and kind of drill down into a more detailed view of how we did this, we thought it was important just to really highlight the business benefits up front. And those benefits were, first, we were able to successfully create this tool and apply it to the North America portfolio. And we identified strategies to save between $5 and $20 million. Next, it was this whole thing around complexity that I mentioned earlier. We were able to really find, really the sweet spot there that balanced cost and complexity, and it wound up for this North America project that 5 was really the best place to land there. And then finally, we were able to create this tool that allowed us to really, search a lot of different ideas and a whole lot of different option spaces to look for different, interesting candidate solutions. And some of the stuff that came out of that was actually the evaluation of new ingredients. And some of those assessments basically, led us to some new technologies that we're progressing right now. Obviously, there's a lot of elements that had to come into place to make this happen. So we had to have a lot of data in order to feed the machine. And so a couple of pieces of data there just to illustrate is we had to have benchmark information on all the different products. So to define the material balances for each, product brand by brand. So maybe Tide, Gain, Cheer, et cetera. You can imagine all the different information on that. We also then had to have material pricing. So that was this kind of first element or first bucket. Next was predictive models. And I already mentioned a few of those. We needed to have models that would allow us to predict things such as the stain removal. And it wasn't just one metric called stain removal, but instead we needed to predict a variety of different types of grease cleaning, food cleaning, beverage cleaning, and so forth. And we had to have that predictive capability as a function of actually the chemistry of the finished products. And then there was user input on constraints and limits. So this was really around how do we define each of those products. And the way that we would do that is we would define, basically what were these cleaning targets brand by brand, and then also density targets to make sure that we would actually have the proper amount in each scoop, right? The final element was the optimization algorithm. This really was what would digest all of these other elements that I mentioned and would help us search through that space and identify solutions that looked good from all angles. An important question that comes up a lot within our company is, how reapplicable is this tool to new problems that might surface, right? So we went out and we created it and we applied it to North America. Can you use it, in the future for other problems? And it winds up that a lot of times the different problems that we deal with often affect the data, which are the red blocks here. Those are things like maybe the material prices, which could change, or maybe even we might want to come up with new benefits for our products, which enters into the different constraints and limits. So it winds up those are pretty easy changes that we can implement pretty easy. These red boxes, are the data ones that are simple. The blue ones that would have been more difficult, the analytic ones, tend to have a longer lifetime, and they're much more general and reapplicable to new problems. A couple of words on predictive modeling, since this is really kind of one of the key foundational elements of models that went into the optimization that you'll hear about shortly. We have two different types of models. We have empirical models and then also semi-empirical models. The stain removal models and whiteness ones that I mentioned earlier, those are examples of empirical models. And then we have density models that were used for predicting density of both common intermediate and also the full finished product. And those were semi-empirical models. In order to create the empirical model, the way we tend to do this is we use software to design experiments for us. So we do kind of classic design of experiment approaches. And in this example, I'm trying to illustrate how we did this for a simple 3-variable case, which is depicted on the right-hand side of the screen here. And you can see that we designed an experiment that's shown in the blue table up here for coffee with 3 different variables. And I've named them V1, V2, V3 to be nice and general. And once we've done that, what we need to do then is kind of populate that table with the actual response information or the actual physical outcome from measurements on this. And the way that we do this in the case of our stain removal models and our other cleaning models such as whiteness is we actually run real prototypes through some standardized protocols such as that depicted on the bottom. And so what this would mean is we would take one of the rows, say the first row off the sheet, which would correspond to a specific prototype. That would be a physical prototype that would be created, and then we would put that into the wash, and what we would do is we would measure characteristics of a standard set of stains both before and after the wash process, and by looking at the color differences between the before and after, we would quantify the removal, and then that would then ultimately be used for training this model. So once you've done that for all the treatments, you wind up with a table that looks like that on the top right-hand side, and that's basically the data set that you use to train the model. We take that data and we go through kind of classic regression type of approaches to come up with a model. And we do this by first a selection procedure where you could use something as simple as, like a p-value criteria or maybe a Bayesian information criteria. That allows us to select which of the parameters, in the model are deemed to be important. And then we would go through a more classic multivariate regression to actually quantify the values of them and ultimately then validate them. When we're done with that, you wind up with a polynomial like that shown here as the SRI model. And that's being shown for a simple case where there's just a few different variables. But the actual models that we used had 16 different input variables, and they had up to 300 different terms in the polynomial. And those were basically the models that then went into the optimization code that you'll hear about in a moment. Just a couple words on the semi-empirical models. Semi-empirical models were things like the density that I highlighted, both for the intermediate and the finished product. The actual functional form from that came out. You can kind of think about textbook, literature stuff that we're just applying from chemical engineering. But then there's actually some empirical parameters that we need to quantify. And in order to quantify those parameters, we use approaches.
what these in terms of the pooling problem, think of these as the inputs. These then go through a pooling stage, which are the intermediate batches, where these premixes are combined to create something from which all the products may take a part of their composition from. And then eventually the outputs would be the products, tide, gain, and so forth, that must satisfy a variety of constraints. Constraints have to do with the product's performance ability to remove stains, so the quality of the product. There are a number of complications that generalize this problem beyond the typical pooling problem that we faced. First one being that when we have to decide the proportions of the intermediate batches that go into the products, that process requires that each product can take from only exactly one intermediate batch. So it introduces a binary variable into this problem. That's not common in pooling. Secondly, there's an evaporation step because we're talking about the powder problem, so powder detergents. So the liquids, the liquid form of the intermediates must go through an evaporation phase that introduces a nonlinearity. The other complications have to do with the performance criteria. So this is it's a highly non-convex, nonlinear mixed integer program. Certainly not an easy problem to solve. So we had to use some innovative approach to be able to address it. So I'll very quickly go over the formulation. This is and I'll put a portion of the formulation up. There's more to it than this, but in terms of a pooling problem analogy, right? I mean, you can look at this as a network, and there's a sort of mass flow sort of view of this, which is the amount of material that goes from one stage of the network to the other. So these variables here represent the mass flow of the premix into the intermediate batch. Then there's a max flow of what's called the additives, the finishing additives. So these are eligible to either go into the premix or directly into the product. And the proportions of those are variables or unknowns. There's the proportion that each product takes from its assigned intermediate batch. There's the binary assignment of batch to product. And finally, there's an evaporation variable. So in the typical pooling problem, the complication is the bilinear term that comes from this X and this V variable. However, here you see it's quite a bit more complex. Now we've introduced another sort of bilinear effect and the discreteness of the binary variable. So, of course, the assignment requirement is that each product can take from exactly one batch. And then there's the typical mass balance equation at the bottom. So that's the basic problem. If I go back to the formulation here, what that objective means is basically the overall production cost. So that the Q's there represent production volume requirements. The CP is the cost of the premixes because that's what's purchased, right? Individual ingredients are not purchased. The premixes are purchased. And then the term in parentheses is the composition throughout the system. Because of mass balance, that cannot go to zero, right? So this is where the total cost of the portfolio comes in. Now, the premixes are sourced, but all of the performance equations and the physical semi-empirical type of equations are in terms of the ingredients that make up that mixture. So we have to apply a little bit more algebra just to get to the premix composition, and then come the additional complications. First one here is evaporation. So that as you evaporate, the water is removed from the system, and the concentration of all the other ingredients increases for that mixture. There's the stain removal index. That's a third-order polynomial, like Kevin said, that can have hundreds of terms. And then finally, the density function. He also showed that. This is typically a target, but we find that it's the best way that we address this is to replace that equality with a tight inequality based on a tolerance. So that's basically the problem formulation. And you can see here the first set of variables highlighted there shows the typical type of bilinear thing that you see in a pooling problem. But then there's more bilinear effects with evaporation. That's new, and it's not something we've seen in the literature addressed in any way. Okay, so obviously this is a complicated problem. The literature for the pooling problem is somewhat helpful, but we found that none of the methods are directly applicable, but we did borrow some ideas. With large-scale pooling problems, typically people will use Lagrange relaxation methods. They may use decomposition. They may use discretization with MILP. There's a variety of approaches. We found that what works best for us for this particular problem is a combination of decomposition with column generation. So you'll see that the algorithm that I described here sort of will have elements of those two approaches. There are 4 main steps, and then we iterate over those. The first step is what we call the singleton step. The purpose is we want to deal with the complication of the binary variable that's introduced into the problem. So what we do is that we simply solve the problem for every single product as if it was allowed to have its own dedicated intermediate batch. So that eliminates the binary variable. It's satisfied by default because clearly this is not a feasible solution. But we start the algorithm this way, and we can calculate these problems because they're in a sort of a parallel environment because they are all independent of each other. In addition to that, what we find is this is still a nonlinear, non-convex problem. It is significantly easier to solve than the original problem because of the elimination of the binary and because it's a more localized. The mass flow of the problem is significantly simpler. And what we have found is that the SAS interior point nonlinear solver is quite adequate for solving this problem and gives us very good solutions that are very close to globally optimal, and typically the local optimal solutions are good enough for our purposes. Remember, here we're trying just to get the algorithm started. So in this case, for example, we start building a set, and the set is going to represent the columns, if you think about this as a column generation approach. So that set A, script A, is going to start being populated with the products, the singleton compositions, which means the subsystem of this pooling problem with all of the chemical compositions throughout that system. And the assignment is given by default. It's actually implied by the grouping itself. In this case, the grouping is a single product. Solve that for all products. You append that to the set, and you're starting to build out these columns. You've got now, in this case, remember the diagram I had before, there were 3 products. So we have 3 members of that set. And then we go to what we call a grouping step. In this step, we've started out now with a set of premixes. And we can calculate a metric that we define called a similarity metric, which differentiates between the chemical composition of these dedicated singleton compositions. With the idea that we then want to group these by imposing a cardinality constraint, which is related to the number of batches that we have available, but minimize the total difference of products within the same batch when they get grouped. Now, this makes perfect sense from the empirical point of view, because if you think about what comes out as final mixtures of this product assignment, we will have products that behave similarly, grouped similarly, and they look similar. They have similar types of compositions. And through experimentation, we see that this plays out in practice, and it turns out that it leads us in the right direction for optimality. So if you think about this case, when we calculate these similarity metrics between the products that we have, since we do have the compositions, having solved the singleton problems, we end up with a situation where, in this case, we've identified P1 as a group and P2-3 as another group. They're more similar to each other than with P1. So think of this as a K-clustering problem, but this is a bipartite formulation, easily solved with a standard MILP solver. In this case, we use SOR MILP solvers to solve it, and it's not a problem at all. Once we get the solution to the problem, we move on to what we call the configuration step. Remember, all we did in the step number 2 in the grouping step was identified a potentially good grouping of products, but we don't know their composition and we do not know their performance. So what we do then is that we solve the original problem on this subset of groups. Now, the implication is because they are a group, they share a batch. And when they share a batch, again, we eliminate the binary variable. And by eliminating that binary variable, again, we benefit from significant simplification of this problem. And again, we find that for the cases that we solve, the interior point NLP solver works quite well. We do use multi-start. Multi-start is required in this case because of the local optimality of because of the quality of the local optima may not be sufficient unless you explore that space a little better. But again, we solve this in a threaded environment because these problems are independent of each other. And we've made enhancements to the algorithm that allows us to, for any problem that we solve, we can improve the local solutions of any subset of that grouping, and we can estimate the cost of any superset. So we're continuously improving the value of these local optima by going through the algorithm and iterating. And then finally, we get to what we call the selection step. So let's suppose that we have gone through a few more iterations and we build out that script A, what we call the group set. And the question then is, how do we select from that set the best combination of groups that satisfy our cardinality constraint, but at the same time minimizes the overall cost? So it's a set covering problem, very simple problem in this context because we have a finite small set of groups. The idea is that as the algorithm iterates, they do a better job at approximating the optimal region, if you think of these this power set of all the groups that we'd have to explore, which would be infeasible to do that. But over time, we start filling out that space, we start doing a better job, and we're selecting the right subsets of groups. Now, in this form, this problem is easily solvable, and it's an MILP, and we use the MILP solver to generate these solutions. And then we return to step 2, and we keep going. So that's the algorithm. Now, a little details that to go back to step 2, we have to introduce a few new constraints to generate additional columns. Otherwise, you may end up with the same previous columns. So this first equation is pretty typical for doing this kind of thing. If you eliminate that alpha, basically what it says is that the new solution cannot have any column, using that term, that already exists in our group set. If you introduce the alpha in the second equation, you relax that some more. In fact, we allow it to be relaxed up to n-1 times, meaning that at least one solution must be new. Now, the reason that it's important to do that is that the idea is that we're generating good candidates as we go along. So if you disqualify all candidates in the grouping step and try to generate new candidates, you will not have at your disposal good groupings that will produce something else by exclusion. So you really do want to you want to introduce one at a time, so that if you have to at most one at a time, so that you can keep improving and you keep getting closer and closer to approximating that portion of the space. So that's it for the math. I want to talk about a few examples that we've brought along. I'll cover the two bullets, the two first bullets, and Kevin will talk about the overall business impact that it's had in the analysis they did for the North American market. The examples I'll cover are to illustrate the performance, the runtime type of performance of the method, and to show the kind of value it delivers. And then I'll show another example with this 22 product instance that gives you an idea of how complexity and cost can be evaluated from an output of the solution, and how you can then use that to make a decision that maybe combines the two objectives or the two requirements. So we solved many instances, but we decided to pick two representative ones for publication. And these two are about the typical size, and these, of course, these problems are, if you look at the size of these sets, they're small for a MILP type of application, but for the pooling problem, this is not atypical of what you see in the literature. Beyond that, these are much harder due to the complexities that I mentioned before. So these are probably as large a problems as we've seen. So in the first case, you have about 21 products, and for each one of these instances, we were able to get a benchmark solution that we could use. And this may have been a historical production run or a best known solution or something like that. And we could use it then to compare and so that we were always trying to meet or beat the performance in terms of the cleaning capabilities and the physical properties of that benchmark portfolio while minimizing the cost. And so the first one, the benchmark had 12 intermediate batches that could be used. The second one, there were 25 products and 13 intermediate batches. So I'll explain this a little bit. The first column represents the number of batches in that particular batch configuration. So if you think about our algorithm, there's a step, the set covering step, that allows me to pick from my option of groupings to satisfy my cardinality constraint. Now, I don't have to set that cardinality constraint to just one number. I have all that information at my disposal, and I can solve it for multiple different batch configurations. I can set that number from 3 to, for example, from 1, which would be one single intermediate for all products, which is very far from a good solution, down to singletons. Every single product gets its own batch, and I can solve for everything in between. And those are very cheap to solve. That's that set covering problem that I can generate solutions for very quickly. So throughout our algorithm, we are updating the values for these individual components as we iterate through, as we improve the objective values that we're encountering. And you can see that the last column is runtime of when we get to the best known solution. So the problems with small cardinality are the toughest problems for the NLP solver. So those take the longest for us to reach a level of quality, whereas with the last one, those are the singletons, and we get that right from the beginning of the algorithm. It doesn't mean that we can't improve it as we go along, because we do keep tightening our approximation. But overall, we see this pattern where a lot of batches solves very quickly. Few batches that takes a little bit longer, but this is one run. Each one of these tables is one run, and then bold is the reference point. It's the benchmark value. So we got permission to show the cost savings, right? So the cost difference from benchmark. So you can see these are very expensive production runs, so that there can be a lot of potential, right? So for the first case, there's a $20 million potential in cost savings as compared to benchmark. For the second one, there's an $84.2 million. So there's quite a bit of potential to save a lot in terms of sourcing these ingredients. Finally, I'll say that the delta column is an estimate of the bound gap. These are highly non-convex, nonlinear problems. Even the subplot problems are. So we really only have lower bounds. However, we are able to estimate what the we only have upper bounds, but we are able to estimate lower bounds. Now, they are estimates of lower bounds. They are not themselves lower bounds. In practice, this gap measure turned out to be very useful, so we use it as a stopping criteria. And I wanted to show another instance just to show this capability of solving multiple batch configurations and what it provides in terms of value. So this is another instance. This has 22 products. The benchmark at 14 batches, intermediate batches. So if you look at just the benchmark comparison, we can lower costs by about $4 million for this particular portfolio. But there's another way to look at this problem, which is for the same performance of the products, for the same quality of products, for the same cost, how many batches do I really need? And that's 6 batches for this particular portfolio. So you can think about, well, the management decision, for example, could be, do you minimize your costs and stick to your plant investments, or do you actually simplify your project, your process, and go with many fewer batches and maintain your costs? There's a trade-off between these two, but between these 2 points, that curve dominates the benchmark in both of those measures. And then also another feature of it is that because of the discreteness of the assignment, there are these plateaus. And the truth is probably that the best solution probably lies in somewhere in the plateau. It's a bit more insensitive to the inputs of the problem, which can vary quite a bit, right? Because these are commodities being purchased and their price can change over time. Okay, so I'll hand it back to Kevin, and he'll talk about the application to the North American market of our solution.
So you can kind of imagine that really if you wanted to fully leverage this new capability, we would need to maybe work in a different way than we traditionally had. And so this slide really kind of helps illustrate this new way of organizing and also the new work process that we utilized really to help us kind of step into this brave new world, so to speak. And so we created what we call this optimization triad. And the optimization triad really helped depict the roles of the different folks that were on the team. This is something that we had adopted actually from some other areas within P&G where we have a modeling triad, we call it. But it looked like this fit with just pretty minor modifications. And that was actually a structure that, has been embraced pretty well within the company. And so we reapplied it here. But we would have functional experts. These tended to be people that had expertise within the formulation area or the process area or consumer area. And they could really help shape, the definition of the problem to make sure that we really, knew what we were aiming at properly. We had data experts. These were people that were really good at actually gathering the input data that I mentioned earlier. These were things like maybe material pricing or benchmark formulations, et cetera. But importantly, they were also really good at kind of visual analytics. So, as we would run these different scenarios, you'd have pretty large, amounts of data to analyze in the back end. And so having folks that were savvy with these different, visual tools like Jump that could, really kind of help illustrate and help you kind of in an interactive way browse that data was very important. And then finally, we had optimization experts, kind of like SAS, the colleagues, Ivan and the other folks there that could really, drill down into the code and, do all the kind of heavy lifting in that particular area. I'm not going to step through the work process, except to kind of mention that, it went from all the way from the problem definition, the very first step, all the way through to the final recommendation. But what was really important to kind of recognize on this is two things, which is one, there was kind of like situational leadership by different individuals throughout that process. So you can see in several of the first ones, there were kind of like the functional experts that owned those steps. Whereas you can see in some of the middle ones, it was kind of handed over to the optimization people, where really they would be leading those steps and so forth. The dashed lines on here, by the way, really represented some of the different recycle loops that could exist throughout that work process. Just to highlight again kind of like the key benefits that came out of this, I think Ivan did a good job of really kind of highlighting how we got to this cost and the complexity trade-offs. But as I mentioned up front, really, we were able to, utilize these new capabilities to, uncover savings in the area of $5 to $20 million across the different scenarios. And then also we identified for our purposes really kind of the best number of common intermediates, which was this 5. And that was kind of this proper balance between the different things. And then finally, having this tool, which allowed us to really, explore this option space so efficiently, is what allowed us to not only identify some of the strategies that we've kind of, obviously talked about here, but also we were able to evaluate some new different technologies, new ingredients that we can incorporate. And actually, those are some that actually coming out of this work, people have committed to in future initiatives. And so these are being progressed. So that's very exciting for us. As far as where do we go next? Well, we plan on reapplying kind of what we've got here to some other regions. Really, again, it will be primarily the data that we'll have to update on this. So, what are the requirements for different products and also the different pricing. But there also will be a little bit of a model updating that we'll do for this as well. It'll be a necessary component there. And then finally, we're looking for opportunities to apply this to other forms, such as liquids and pods. And I think that pretty much summarizes our presentation. And so what I'll do is I'll pause, and I guess we can now take care of questions from the judges and then other folks. So.
Thank you.